Hello all, welcome back to another video tutorial. Today's topic is nanomedicine in the management of Alzheimer's disease. Let's start with introduction, as we all know that Alzheimer's disease is a significant health concern, particularly among the elderly population. It's characterized by progressive and slow brain decay, primarily caused by the formation of extracellular plaques in the hippocampus. The incidence of Alzheimer's disease is rising worldwide. Recently, more than 50 million people were affected with Alzheimer's disease, and this burden is continuously rising. This could have a big effect on the world economy and the workforce. Dealing with the pathology of Alzheimer's disease comes with various challenges. Drugs aimed at treating the cognitive impairments associated with Alzheimer's disease typically target neurotransmitters or enzymes. They are often delivered to the brain via the intranasal route. However, these drugs face limitations. They may fail to be effective due to issues like poor absorption into neuronal cell membranes, instability, brain toxicity, and other factors related to their absorption and effectiveness in the body. Pathogenesis of Alzheimer's disease. Understanding the development of Alzheimer's disease is crucial for identifying targets for effective therapy, especially in the early stages when changes may still be reversible. At the onset of Alzheimer's disease, key features include the formation of intracellular neurofibrillary tangles and extracellular amyloid plaques in the brain. Histopathological changes involve neuronal loss in the hippocampus, synaptic degeneration, and aneuploidy. Additionally, early pathophysiological modifications include neuroinflammation, oxidative stress, microbial infection, mitochondrial dysfunction, and compromised brain lymphatic system. Various physiological factors contribute to the onset and progression of Alzheimer's disease, including lifestyle and age-related factors such as hypertension, diabetes mellitus, elevated homocysteine levels, inflammatory biomarkers, and obesity. Understanding these factors is crucial for developing effective interventions against Alzheimer's disease. Limiting factors in drug delivery to the brain. Role of blood-brain barrier in the pathogenesis of Alzheimer's disease. Imagine the human brain as a fortress guarded by two specialized barriers, the cerebrospinal fluid barrier and the blood-brain barrier. Now, the blood-brain barrier is like the gatekeeper, crucial in Alzheimer's disease. In Alzheimer's disease, problems with the brain's blood vessels can cause memory loss and confusion, potentially leading to amyloid buildup in the brain. The blood-brain barrier controls what goes in and out of the brain, including these amyloid proteins. But when the blood-brain barrier falters, it lets too much of these harmful proteins in, leading to brain damage. It's like the gatekeeper falling asleep on the job, letting intruders sneak in and wreak havoc inside the fortress. This protective barrier consists of layers of vascular endothelial cells tightly sealed together, with support from astrocytes and microglial cells keeping a watchful eye. Special transport proteins help move molecules across the blood-brain barrier, ensuring only the right ones get through. Nose-to-brain drug delivery and limitations. Imagine drugs embarking on a journey to the brain, starting from the nasal route. It's like a scenic route, with twists and turns, all leading to the brain's doorstep. This journey begins as drugs move through the respiratory epithelium, aided by the trigeminal and olfactory nerves. Their destination: different parts of the brain, like the frontal cortex and cerebrum. Now, there are two ways drugs can travel: intracellular and extracellular. Intracellular travel is like a slow train, taking about a day to reach brain cells. It starts with drugs being taken up by olfactory sensory neurons and peripheral trigeminal neurons, then moving through nerve cells to reach various brain regions. This route is perfect for drugs coated with lipophilic molecules. On the other hand, extracellular travel is the express route. It's the fast track to the brain, with drugs zipping through intercellular clefts in the nasal epithelium and along neural pathways. Once they reach the brain's doorstep, they have different options: entering the bloodstream, nasal lymphatic vessels, or even hitching a ride with olfactory nerve bundles. But this route has its challenges, like the physiochemical properties of drugs and the nature of nanomedicine carriers. Despite these challenges, researchers are working tirelessly to improve drug delivery to the brain, ensuring drugs reach their destination safely and effectively. It's a journey filled with obstacles, but with each discovery, we're a step closer to better treatments for brain diseases like Alzheimer's. Nanomedicine's approach for drug delivery through blood-brain barrier. Think of nanomedicines as tiny superheroes, equipped with unique abilities to deliver anti-Alzheimer's drugs right where they're needed in the brain. These miniature marvels have some remarkable advantages, like being incredibly small, 100 to 10,000 times smaller than a human cell, which allows them to easily interact with cell surfaces and even enter cells themselves. They're like stealthy agents, equipped with central core structures that can encapsulate drugs, ensuring their protection and prolonged circulation in the bloodstream. But that's not all. Nanomedicines are also highly specialized, capable of targeting specific cells or even intracellular compartments, like the A-beta protein in Alzheimer's cells. This means they can deliver drugs directly to the site of the disease, reducing the need for high doses and frequent treatments, which is great news for patient compliance. Despite some challenges, nanomedicines offer a host of advantages over traditional drug delivery methods. They're brain-friendly, stable, biocompatible, and biodegradable. They protect drugs from being broken down too quickly, ensuring they stick around long enough to do their job effectively. Plus, they can control the release of drugs, providing a steady supply where it's needed most. The figure demonstrates how functionalized nanoparticles have been employed to overcome the blood-brain barrier, exploiting different transport pathways to achieve anti-Alzheimer's disease effects of the delivered cargoes, such as A. Transport of nanoparticles through cellular transport proteins. B. Transport of nanoparticles through tight junctions. C. Transport of nanoparticles via receptor-mediated transkitosis. D. Transport of nanoparticles via transcellular pathway following diffusion, specifically adopted by gold nanoparticles. E. Transport of cationic nanoparticles and liposomes via adsorption-mediated transkitosis. To manage the pathologies of Alzheimer's disease, different nanocarriers have been used, such as gold nanoparticles, lipid-based nanoparticles, polymeric-based nanoparticles, nanomicellar, dendrimers, and nanogels. Thank you for watching. See you soon with another interesting topics.